Hey folks, welcome to your very first set of 8th grade science video notes. This is the first lesson of the first unit for this 8th grade science class, which is mostly aligned to the 2023 Indiana Academic Standards for Science. In this lesson, you'll learn a bit about what we call the nature of science. You can also think of it as some general science basics that you'll need to know for the rest of the year. More specifically, here's what you should be able to do by the end of the lesson. They aren't exactly Indiana standards, but they're my standards. You should be able to describe the difference between science and pseudoscience and list some examples of each. You should also be able to distinguish between a scientific theory and a scientific law and describe what empirical evidence is and how we collect it. It's also important that you understand the difference between an observation and an inference and be able to tell what good data is and be able to describe its accuracy and precision. Lastly, you will need to know the parts of a graph and how graphs help us to show the data we've collected and recognize relationships or patterns in that data. All right, let's get started. First off, what is science? There are several definitions for science that you can find, but for us, we're going to define it as the study of our natural world, the phenomena or events that happen in it, and our explanations for why those phenomena happen. The most important thing to know about science is that it is based on real scientific data. The purpose of science is to better understand our world. Good science does not come with any other goal or biased intentions. It's simply there to help us understand. Some examples of science fields are astronomy, the study of planets and other bodies in space, chemistry, the study of matter, biology, the study of living organisms, and environmental science. Basically, anything you can think of that you know scientists have spent a lot of time studying and collecting data on, it's probably a science. Pseudoscience, however, is quite the opposite. Pseudo is a prefix that means false, and it's used to describe something that appears to be something else but actually isn't. So pseudoscience might look like real science, but it's not. People that are pushing ideas that are pseudoscience might make it look convincing by showing some set of data, but the data they often show is collected incorrectly or possibly represented with some kind of bias that's not scientific. Pseudoscience can often have other goals, like convincing people to buy something, or convincing people that someone's out to get them, like conspiracy theories. Some examples are astrology, like horoscopes, hypnotherapy, like you're being hypnotized to help you break a bad habit, the flat earth theory, or acupuncture, all of which have no concrete scientific evidence that they are true or effective. Scientific laws and scientific theories are both ways in which the science we do gets presented to the world. They're both based on real scientific data, often after years of collecting that data. A scientific law is usually a fairly short statement that describes what happens, or presents some consistent patterns that we see in our world. It does not attempt to explain why the thing happens, just what is happening. Generally, laws are considered as fact. They are always true and they do not change for the most part. Occasionally, laws can change just a little bit when we can make better observations and use those to describe the events that we see in a slightly better way. But for the most part, they stay the same or very close to the same forever. You may have heard someone say, "I've got a theory," which is an appropriate way to use that word in normal everyday life. It usually means I have a guess at an explanation to what happened or will happen. They're usually just guesses based on gut feelings. However, a scientific theory is not a loose guess. It's a well thought out explanation for how and why the things in our world do the things they do. Scientists will collect data and analyze that data to find patterns. Then based on those patterns and the different variables they change in their experiments, they're able to come up with the explanation for why the patterns they observe are occurring. If you haven't noticed, in the last 40 years, technology has changed drastically. As our technology and data collection tools get better, we can collect better data and come up with a better explanation for why certain things happen. This means that with new evidence, scientific theories can easily change because they're just the best explanation we're able to come up with using the data that we have at that moment in time. An example of a scientific law is the law of evolution, which basically says that over time, a species will change and look at least a little bit different. That's just an observation of what happens, right? However, Darwin's scientific theory of evolution by natural selection is an attempt to explain why the species evolved. Darwin explains that some members of the species have certain traits that make it easier to survive in their environment. When they live longer, they're more likely to reproduce and more likely to pass on their traits to the next generation. So, over time, the members of a species that don't have those helpful traits tend to die out, while the ones with the helpful traits thrive and multiply. Empirical evidence is just a fancy term for data. The word empirical comes from the Greek word empiria, which means experience. Empirical evidence is the data we collect through some experience, usually an observation or an experiment. Observations are just things that we take note of that we experience through our five senses. Experiments are tests that scientists run, changing something about the experiment to see how the results change. Scientists take measurements or make observations about their experiment, and that is their data. Observations, as we said, are one way to collect empirical evidence. Generally, observations are "here's what we see" statements. In that way, they're kind of similar to scientific laws. They just describe the things that we see. Inferences are educated guesses about why things happened based on the data that we have. They're an interpretation of the data. They usually come in the form of "here's why I think this happens" statements. In this way, inferences are kind of like scientific theories because they help explain why things are happening. So now you know how we collect data, you probably need to know what is good data and what is not, right? There are two classic ways which we can describe data. We can describe its accuracy, which is how close the data is to the correct answer, and we can describe its precision, which is how consistent the data is, or how many times you can get the same data by doing the same experiment. Data can be both accurate and precise, where it's correct and you get the same answer multiple times. It can be accurate but not precise, where the average of the data is close to the correct answer, but your data points might be far apart from each other. Data can be precise but inaccurate, where you get the same results over and over again, but they're not correct. Or it could be neither, where it doesn't average out to the correct answer, and the data points are far apart from each other. Now's a great time to glue in your accuracy versus precision chart and draw X's on it like the one on the chart shown here. Graphs are the #1 way scientists can represent their data in a way that's easy to read and recognize patterns in the data. You should already know how to graph points on an XY scatter plot. As a reminder, the x-axis is the one going left and right, and the y-axis is the one going up and down. What I want you to know is how to label a graph correctly. Each axis needs numbers, obviously, but they also need a title, so you know what those numbers mean. Axis titles also usually include the units for that data. At the top of the graph, you place a graph title, which is often just whatever you call the y-axis versus whatever you call the x-axis. In this case, the graph is called motivation versus days at school, because motivation is the y-axis and days at school is the x-axis. If you're placing more than one set of data points on a graph, you also need a legend or key that tells you which data points or which line is which set of data. In this case, my key is color-coded, but you could also have different line styles as well. And of course, you need to include the data. The data usually starts out as individual points, but scientists usually either draw a line from point to show the changes, or draw one straight line that hits most of the points, called a line of best fit. Now's a great time to glue in your parts of a graph paper and fill in the blanks with the words that you have to cut out. Well, that's all for today, folks. I hope you listened closely to this video and you wrote down all the information that you need. If you have any questions about these notes, feel free to ask.